Hi, I'm Doug Milne. I'm an Immersion Days educator at the National Canal Museum, and I'm going to explain a little bit about buoyancy. Normally, when we do this talk, it follows a discussion about friction. And the point of this discussion is to find out why we used canal boats in the first place. Why not just load up the heavy stuff we wanted to move from the Poconos down to Philadelphia on a horse and cart and take it along and get it where it's going? Well, the reason for that is that they needed to move a lot of heavy weight. And the easiest way they discovered to move that weight was by water. The reason for that is that friction is greatly reduced on the water, and so you can move a lot more weight over water than you can using the same amount of force by moving things with a horse and cart. The typical cart of the time loaded up about 10 tons of material, but it took 6 to 8 horses or mules to move that material. On a boat, you can move the 10 times that much weight, 100 tons of material, using only 2 mules, because there's so much less friction on the water. Also, they didn't have to run into things like rutted roads, mud, things that had fallen across the roads, anything else that might impede their progress. But in order to load that 100 tons on the water, you have to understand about buoyancy. Buoyancy is basically broken down into a couple of different things. One is area. You find area by multiplying length times width. The other is density. How heavy is an object based on its size? A rock is going to be heavier than a piece of wood the same size because it has more density. So, I have 2 objects here. I have a brick made from clay, brick, and a boat made from wood. This boat is not hollow, it's a solid piece of wood, but it's still made out of wood. Now when I ask people which of these 2 things is heavier, usually they guess the brick is heavier than the boat. Well, I have a measuring instrument here that will let us find out for sure exactly how much these 2 things weigh. If I put my brick on the scale, you can see that it weighs almost 2 pounds. If I take my boat and I put that on the scale, well, a lot of people will say, hey, it's made out of wood. It must be lighter. But in fact, you can see that the boat weighs almost 1 pound more than the brick. The next question I usually ask is, if I take this brick and I put it in the water, is it going to float or sink? A lot of people guess sink, sometimes people guess float, but the fact of the matter is, it sinks like a stone. Some people will guess that this brick sinks because there are holes in the brick. Well, holes are obviously going to let air in, and that'll make almost anything sink. But the fact of the matter is that this brick, even if all the holes were filled, would still sink, because the material it's made out of is too dense for the water underneath it that it displaces to hold up, to create buoyancy. So, whether this brick is solid or it's got holes in it, it's going to sink if I put it in the water because its density is too great for the water to support. Now, we know that this boat weighs almost 1 pound more than the brick. If I asked most of you if this boat was going to float or sink, well, some people would say, hey, it's a boat, of course it's going to float. Other people would think, hey, it's 1 pound heavier than my brick. Maybe it'll sink. Let's find out. If I put this boat in the water, it floats exactly the way you would expect a boat to float. And the reason for that is that there are 2 things in play. One is that the material it's made from is less dense than the material that the brick is made from. Wood is less dense than clay or stone, and so it is more likely to float. The other thing that is in play is that the boat is clearly a good deal larger than the brick. It covers more surface area. its length times width, its area, is larger than the brick. Now the fact of the matter is, if you increase the area of an object that is too dense to float enough, you can make it float. If I could take this brick and I could flatten it out and make it wider than it is and longer than it is, it would still weigh the same. It would still be made out of the same material. But eventually, you would get to a point where its surface area was great enough that the displacement it creates by being placed in the water would allow the water underneath to make this brick float. Likewise, if I took this boat and I could somehow smash it down and make it smaller than it is, less sizable, covering less area, it would still weigh the same, but because its surface area had been reduced, eventually the density of this object would overcome the density of the water that was trying to support it, and this boat would sink to the bottom of what would ordinarily be a canal. So, what we discovered over time, what was discovered back in the old days, was that if you can make a boat big enough and broad enough, you can load it with so much weight that the friction of the water, which is a great deal less than the friction created by moving wheels over land or a heavily laden cart, is such that you can move much greater weights using boats laden with whatever you're trying to move than you can move over land using a cart and horses. In fact, 100 tons of material could be loaded onto a 20-ton boat and could be pulled by only 2 mules. And most canal boat drivers had only 2 mules, so they kept them in good repair, they kept them fed, they kept them happy, and those mules worked for them for an 18-hour workday, 6 days a week. The canal was closed on Sundays, and they would pull about 22 miles per day. So the same loads could be moved much faster by water than they could by land, and that is why we had canal boats. Thanks for joining us today, and I hope you'll join us for our next video. My name again is Doug Milne, and it's been a pleasure visiting with you.